hear us yet or no?
Hello? Can you hear me? Is it good?
You got it?
Is it good?
Both of us?
Awesome. Okay. Welcome, everyone. Thanks for coming in to listen. My name is Evan Long. This is my 4th year as a member of Team 1678 and my 2nd year as design lead.
My name is Anthony Diaz-Vigil. I've been with 1678 since 2010, and I've been mentoring for the past several years on the mechanical side of things.
So we're going to talk to you guys about design with 3D printers. So to give a quick overview of the presentation, just kind of what topics we're going to talk about, we're going to start with some 3D printing technology and kind of why it's relevant now and where the technology is at. We're going to talk about some physical limitations of 3D printing, so kind of the rules you have to follow if you're going to print a part. We're going to talk about a printing toolkit, so some common design features that you guys can use if you wanted to design a 3D printed part. Some modeling tips, just why modeling for 3D printed parts is a little bit different and kind of what's important about it. Some printing variables, so the settings that are common on a lot of 3D printers that you can change to increase the effectiveness of your parts. And lastly, some examples in FRC, so some things that we've done in the past on Team 1678 that have worked pretty well. Before we get started, I just wanted a quick disclaimer. I don't claim to be an expert on 3D printing. I have some experience with it, and I've done a little bit of research, but if you guys have questions or clarifications or something to add, just raise your hand, and I can answer them.
Cool. So a brief history of 3D printing. In the 1980s in Japan, at a university, I forget the university, researchers were playing around with lights and polymers, and they discovered that there was an application for bonding monomers into long chains of polymers based on the shape of the light. So basically, a monomer is just a chain of hydrocarbons, and it has an internal bond where it links onto itself. So if you expose it to ultraviolet light, it breaks that bond, and then it can bond to another monomer, forming a long chain of polymers. So that's where the word polymerization comes from. It's just binding those plastic chains together, and they began to play around with that. After that, in the mid 80s, they added to that, and they came up with stereolithography, and that's where the STL and the STL format comes from. But basically, you're doing the same thing, but you're using a laser to focus on a smaller area in order to get more precise bonding in the areas that you want, so you can make a 3D figure. After that, FDM machines were invented. FDM is what most people are accustomed to. It's where you actually are extruding or adding a solid material piece by piece and building up a structure in layers. And then in the early 90s, laser sintering and laser melting 3D printing became popular, with the difference being sintering just gets the metals hot enough to bind. So it's more applicable in printing alloys, and SLM gets the material to melt completely, but that's only applicable for single metals. And then finally, in 2009, the patent on FDM manufacturing expired, meaning that any company could create their own 3D printers using that technique. And that's why at the end of the 2010s, you ended up having a bunch of different companies coming out with a bunch of different printers at that time. And then the image right there is an obsolete type of printer called a laminate printer. And basically, you had this large sheet of thin plastic, and it would lay an entire layer, and then it'd cut that layer out, and then it'd lay another entire layer on it with adhesive. And you'd end up with this 3D printed part cut layer by layer, but you'd have a ton of waste material. I thought it was just an interesting thing that's completely obsolete now. All right, so back to 3D printing types. Stereolithography, that's where you're using light to build up chains of the polymer, usually from a liquid. Fused deposition modeling, FDM, that's the standard 3D printing most people are accustomed to, like little plastic 3D printers most of you guys have in your own shop. Selective laser sintering, that's where you have a powder bed usually, and you're shooting it with a laser to get the metal hot enough to bind to itself. And then selective laser melting, again, that's a step further, and you're completely melting the metal. So common printers in FRC. Some of the most common FDM printers, there's the Prusa i3. That's a good bang for your buck printer. The Markforged makes several. They make the Onyx 1 and they make the Mark 2, MakerBot, Ultimaker. And then in terms of SLA printers, there isn't really that many that are applicable to FRC. The main one that I've seen teams have is made by Formlabs. But there are some disadvantage to SLA, and there is a reason that the FDM printers are much more popular. So FDM versus SLA. FDM, the advantages are there's a huge range of printing materials you can supply from lots of people. The materials are cheaper, and the parts end up being stronger overall. The advantages of SLA is that they come out higher resolution. You're not limited by a print height of the filament being extruded from your nozzle. So you end up with a really nice smooth surface. The downside is most of these materials are very brittle and they're not as strong. So in FRC, that's typically you want stronger parts, and those parts won't survive it unless they're used for like small mounts and stuff like that. So we have some common 3D printing materials. Lots of people use ABS, PLA, and nylon. And then if you go to the next slide. Yeah. So a little bit more detail about them. ABS has a long lifespan. It's hard. The yield strength is 7,500 approximately PSI, and the ultimate tensile strength is 10,000-ish PSI. If you look at the little graphic, that's a nice way to visualize it, the differences between the three materials I'm talking about. So all of them have kind of been put into the same scale, and then they're compared to each other. Nylon. Nylon is also very popular, but there are a couple of issues with it, mainly warping. It is flexible and it is tough. So if you want something that's impact resistant, nylon could be the way to go. And here's the comparison of the yield strength and ultimate tensile strength. And then if you look here, the durability is as high as possible. In terms of resisting impact, it is really, really good.
By the way, all these slides are going to be posted online after this. So if you want to just get those later, it's also an option. Okay, so as much as I wish it was, 3D printing is not magical. It can't just do everything. It does have its limitations, just like any fabrication process. And so while it might have less limitations than, say, a mill or a lathe, they still are there, and it's important to know them if you are going to be designing with 3D printed parts. So the first one is the most obvious one. Your part needs to have some kind of surface that can stick to the print bed. If you don't have a surface, or if your surface isn't big enough, halfway through the print, your part will dislocate and move off the table, and then you'll end up wasting a bunch of material and ruining your print and wasting a bunch of time. So most commonly, the solution to this is you just pick flat surface on your part and stick it on the table, and that's all it takes to it. Sometimes you'll find that there's not a easy flat surface that you can use on your part. Maybe it's a round part or a sphere, something like that. And there are still a couple options. You can add a brim to a less than ideal surface. You can break your part into two little components with flat surfaces and put them on the bed and assemble them later. Or you can also do this thing called raising apart, which you can see in the top right picture right there, which is basically where you print a temporary structure underneath it in order to build up that adds a surface against the print bed, but you can still have a complicated part. The second one is that 3D printers are inherently limited on the amount of overhang they can print. So you can think about it that with every layer, they basically need to have something underneath it to extrude the material on. If they don't, the material will just fall to the ground as the extruder is moving up. And so generally they can print 45-degree angles up, but not anything more than that. They're limited to 45 degrees. And so to solve this problem, most printers print what's called support material, which is basically just a temporary structure that they are able to print on afterwards that you just take some pliers and remove afterwards. And most of the time, you just click a little box that says, I want to add support material to this part, and that's all it takes. Occasionally, though, there are some cases where you want to add interior features where you can't get pliers to remove the support material. You can't get inside there. A good example of this is like a zip tie path. If you have something curving around on the inside, maybe you need to have the zip tie come back out towards you, you're not going to be able to remove the support material in there. So you do still have a couple options, though. You can pause the print right before the overhang and actually remove the support material manually and put the zip tie in there directly, and it'll print on top of the zip tie. And it's a little bit sketchy. It might not work. You might need to play around with it a little bit, but it is possible. Or the other one is kind of a weird trick. You can add a little bit of a roof to whatever interior feature you have in there. You can see like those bottom pictures right there. If you add a little teardrop shape, you can extrude any feature you want. Because that's more than 45 degrees, it's not going to need any support material. So this slide is less about limitations and more just kind of considerations when it comes to 3D printing. So naturally, the way that FDM printing works is you heat up your plastic and you put it on the print bed, but then it cools. And during this cooling process, it tends to shrink because it's going from hot to cold. And so most of the time, this doesn't make a big difference, but a couple places where it does affect is with holes. If you try to print an exact diameter hole, it's going to come out a little bit smaller once you bring the part off the bed. So some printers have some things that can help deal with this, like some heated beds or heated enclosures. But most of the time, the easiest solution is just add 10 thou in your model. Just make the holes a little bit bigger, and then they'll come out the right size, or maybe whack it with a drill. If you really need a precise hole, you can print what's called the unit test, which is shown here, which is just printing a bunch of holes and measuring how they come out relative to what you're expecting them to be, and you can kind of scale your holes relative to that. And then the same shrinking force can also cause part warping along the print bed. You can see how that bottom part right there is popped up on one side. And this is especially with really long parts. And the idea is that as it's cooling, it's going to be shrinking. But if it's really long, it's going to all shrink together and kind of pop up off the bed, and it can dislocate. And so the solutions can be add a little bit of adhesive, add a brim around the part. A brim is just kind of like an extra surface that helps it stick. Or another small trick is you can fillet the vertical edges on your part, because that kind of helps remove stress concentrations. Those are the most likely things to pop off the bed.
And then if you guys take a look at the unit test, not only is it testing the hole in one direction in the standard up and down print direction, but it actually has the three Cartesian planes. So I was having trouble pronouncing that. So it actually, it's testing the 3D prints in all directions so that the warping in each direction. It's something that you have to take into account when designing stuff.
So definitely, this next point is the most important one when it comes to limitations of 3D prints, and this is layer adhesion. So the idea is that as a printer is printing along, within a single layer, it can make that layer super strong. It can extrude a single strand and have all these crisscrossing patterns and everything. But between layers, it's limited on just how well it can get each layer to stick on top of the one before it. And so this can cause a bunch of problems because those in between the layers is always going to be weaker in shear than anywhere else in the part. And at least on 1678, the majority of the part failures that we had from 3D printed parts were all layer shears. They were all parts breaking off across these layers. And so you need to be a little bit smart about how these layers are printed. Over here, I have some examples of when this affected us on 1678. Both these pictures on the left were my first attempt at printing a part. Both of these failed. In this case, these horizontal holes right here blew out because there were some bolts in them. And this one right here, it was supporting a tube coming off at an angle like this, and the whole thing ripped in half when our elevator was flopping around for a little bit. But then I went back, and all I did was just rotate these parts 90 degrees and change the orientation of them. And now you can see on this top one, the layers are going to be going around those holes. And on this one, there's no longer going to be layers in the direction that there's shear. And neither of these second parts failed. So this is kind of an example of why this is really important, because the same part just rotated on the print bed can really change how it performs on the robot. And so the solution to this, you can't actually change the layer adhesion or how well it sticks, but you can think about where you want this weakness to be in all your parts. So it's a good idea just from the beginning kind of think, where do I want this weakness to be? Where is it okay for this to be a little bit weaker? And then you just design your part knowing, okay, I need to have it in this orientation when it goes on the print bed. And then lastly, I just wanted to give a quick warning, and this might seem kind of obvious to some people, but it wasn't obvious to us last year, so learn from our mistakes. But just know the limits of your printer. Printing is not meant to replace aluminum or steel or anything like that. It's just not how it's intended to be. It has its limitations. An example of this was last year on our wrist, so the thing that moved our cubes up and down on our robot. Inside we have some little pulleys that were printed, and of course, right at Champs, in the middle of our matches, the hex profile on those pulleys rounded out. And we had to run a couple matches without our wrist, and then we had to rip the entire robot apart, swap those pulleys out, put the whole thing back together. It was a huge pain, all because we thought we could get away with some printed pulleys. So just a warning, make sure that you aren't overextending your limits.
All right, so we've put together a little bit of a 3D printing toolkit that has a bunch of common features that are common to 3D printing. The first feature I'm going to talk about is ribs. Basically, if you guys have ever taken apart electronics, you've seen ribs. Ribs are where usually when you have a shell, something that's hollow, the reinforcements that run along in any direction inside of that shell. So here's an example of a rib. Another thing to note is when you're 3D printing and whenever you're machining something, make sure to include a radius. This picture doesn't show it, but normally the radius helps distribute the load nicer. So if you're putting ribs in, be sure to have a nice round curve in there. Additionally, lugs are important. If you're printing multiple things that go together, the lugs help share the load between the two pieces that are being combined better than if you're to simply glue them and stuff. It helps translate a lot of the force into the actual material rather than just relying on the adhesive. Next one. Yeah.
Those things that pop up out of the part of lugs.
Yes. All right. So bosses. Bosses are also very common in injection molding. A lot of the features that you use in 3D printing are similar to those that are used in injection molding, but you don't have the limitations that you do in injection molding, like overhangs and stuff. In here, you can see a boss. This picture is taken from an injection molding company, but if you look, it has a taper on it. Boss is just the cylinder that comes up that you put screws into, and you don't have to put the taper onto it for 3D printing because you don't have to take it out of a mold. Over here is some geometry for the boss. Basically, you have the radius part, so it has improved strength. And then something to keep in mind is the hole sizing. Normally, when you're creating the hole, you just go for the internal diameter of the bolt, the smaller diameter. But because of the hole shrinkage, you'll probably have to play around it up the size a little bit. Typically, you aim as close as you can to that. And then you use a sheet metal or self-tapping screw, and those will cut into the plastic itself. So our boss is the actual feature that comes up, and then you thread a screw into it. And then in addition to that, if you need even more strength, you can just do a self-threading hole, which is a solid feature inside of the 3D printed part itself. You don't have to just have that extruded piece. It can be completely solid around it. Insert nuts. So there's a couple different ways to do these. These are really strong and fairly simple to implement. If you look up there, there's that was a pause print, and you can actually insert. What you do is you make a hexagonal profile, the same as the nut that same size as the nut that you're going to be using. And you can actually place it inside of the 3D printed part and continue to 3D print around it, so that when you need to bolt your part to something, you can simply screw into it. A couple of tips when doing that: use 3D printed or use super glue, because it helps to keep the part in place if the part happens to become dislodged when the part is complete. Then there's no way of recovering that. The super glue helps not only by retaining it in place, but it stops it from rotating in shear along the face by providing a shear force along the face of the flat sides of the nut, and then that kind of helps the material stop from deforming. There's a couple other types. So on our drum for our elevator this year, we used a piece of extruded tube, and then to power it, we actually made these plugs that were part plug, part pulley. And if you see right here, it's kind of hard to tell without rotating the model, but these are long slots that go along this direction into the board. And what we did was we just made the size of the nut as a rectangle and extruded through, and then the very end piece was the other half of the nut, so it's hexagonal. And then we placed the nuts in, super glued them in place, and these round holes right here these round features right there are holes, so you could actually bolt in from the outside of it, and that allows you to transmit torque between the tube and the plug itself. Cool. Additional features, like Evan was saying, zip tie paths are really nice for mounting for electronics and stuff, but in here you can see a bunch of internal features that would need support material in order to survive, and then there's no way to actually remove that support material nicely. So what you want to do is, again, make that to your shape so that it can go all the way through, and then you don't have to worry about the zip tie channel collapsing on itself. And then another thing is snap fits. We experimented with these a little bit in the off season. Something to really keep in mind is that the direction that it's printed in is critical, like on this. If you print it with the layers going in this direction, you end up with a giant moment. So it's like a torque in that direction that wants to peel the layers that are just melted together apart from each other. And those snap off very easily. So whenever you're making one of those, make sure that the layers are going perpendicular to it. In addition to that, modeling them is a fairly difficult stress analysis problem, because normally you have a different length and you have different materials, and the 3D printed materials don't always exactly line up with the like known textbook values of the plastic. So you kind of have to play around with them before you get them correct. So there's some other things you can do. Part fixtures. If you're gonna machine a lot of things, if you're gonna machine a part repeatedly, and you know that, you can actually make fixtures that make it easier to put into whatever mill or lathe you're using. And then, yeah, that ends up saving a lot of time and a lot of stress. If you look here, there's actually no good way to clamp onto that part and keep it consistent. So there's a fixture made for it where you just insert it, you clamp down, and then you can machine that repeatedly. In addition to that, you can 3D print molds. So I'm not sure if you guys are all familiar with SolidWorks, but whenever you design a part, especially in plastics, in the plastics tools, you can actually form a shell around it. So you end up with the negative of whatever part you designed, and then you can 3D print that, and you can use it to cast different materials.
One thing I wanted to add is just kind of a possibility. Disclaimer, I haven't actually tried this, but it would technically be possible. So if you guys wanted to pocket some large 20 DP gears on your part or on your robot or something, you want to save a little bit of weight. Normally it's not an easy thing to do because you can't just clamp a gear into a mill and expect to machine it out. But it would be possible to print a 3D printed fixture for it so that you could slide the gear into this little 3D printed fixture and then you could pocket out the gear. So it would be kind of cool to do. So normally I would try to avoid talking about modeling in a design presentation. I kind of believe that those concepts should be a little bit separate. Design is the ideas that you come up with, and modeling is just how you express them in the computer. But unfortunately, when it comes to 3D printed parts, sometimes the parts can be a little bit complicated. So modeling can be an actual challenge on its own. So the first concept I wanted to talk about is this idea of resilient modeling. So in the past, I have modeled a couple parts, 3D printed parts specifically. I've had over 100 individual features in a single part file. And when you have that many, it can be a huge pain, and you need to have some kind of organization. And so one way of organizing these parts is with the resilient modeling. And so resilient modeling basically just means that you can go back and edit it at any time, and you'll still kind of preserve the structure of the part. And it's kind of all about your time. If you're wasting time resiliently modeling, you're kind of doing it wrong. And so for an example, I want to talk about these gearbox plates here because this kind of illustrates how it can be done. The idea is you start with kind of a master sketch of all the critical design features that you know where they are, and you can go back and edit them at any time. Then you make a really basic extrude here, just a really basic core features. You guys can see that's just a bunch of rectangles with holes cut out in them. That did not take me very long to do, but I was still able to fully assemble this gearbox model right here. I was able to add in all the parts and verify that it was going to work, and I could get mentor feedback on it and see that it's going to work. And if I find something wrong, I can easily go back and redo it because I didn't spend too much time on it. And then you build out from there and kind of go over all the details like pocketing and fillets and mirroring and all that stuff. And this way you're not doing all the pocketing multiple times over every time you need to make a change. You're only doing it once at the end, and you're saving time. And you're not going to have sketches referencing small details like fillets and that kind of thing that might break your model later. And this is, of course, not about 3D printing. This is a gearbox right here, but the same concept can be applied. And then you can kind of see that in this next slide. So I don't know if you guys are familiar with multi-body part modeling in SolidWorks or whatever platform you guys use, but I have found it to be super helpful when it comes to modeling 3D printed parts. So the idea is you can model just kind of the material you need on the 3D printed part, just some material around a bolt there and maybe around a bearing, and then you can kind of bridge these materials together with the next one, and then add all your details to it. And this ensures that you're not wasting time with all the details. You can get the core materials down first. They're always going to be there. They're never going to change. And it's really easy to just quickly mock up a part doing it this way and throw it in assembly, verify that it's going to work, and then later go back and add all the details. This kind of Well, so another way that you can use multi-body part modeling as well is if you have a lot of interconnected parts. So if you're making a mount for an electronics part, or maybe you're having parts that are meant to assemble together or move around together, sometimes it can be a huge pain if you model them all in separate part files and then throw them together in an assembly. It can really make things difficult, and if you want to make a change to it, you have to edit all those individual part files. But SolidWorks does actually have the capability to model all these parts together in a single file, and that way they can all be referencing the same sketches and that kind of thing. And I find this to be super helpful. And I know that other platforms have similar ideas too, and things like Onshape are kind of built entirely around this idea. So I think it's kind of cool. And then this last slide about modeling is getting a little bit specific, so I don't want to spend too much time on it, but these are just kind of cool tricks that you can do to help with modeling 3D printed parts. The first is a shell. A shell is a super easy way to remove a lot of material in your parts. You can quickly model the part, knock out one face on it, and then remove all the material on the inside. And it can make some pretty complicated cuts in a single feature. And it, most of the time, the most important material is the stuff that's around the outside anyway. The material that's on the inside isn't doing a whole lot. And so when it comes to pocketing, rather than wasting time, adding out, cutting out material and all that stuff, I'm in the habit of just, shelling out the feature. And it can really save a lot of material and a lot of time too. Another cool one is the loft. I can't say I've ever used a loft outside of 3D printed modeling, just because it's kind of a weird feature. The idea is you make a connection between two, profiles that you define. And while they make weird profiles, so they're not really suited for machining on a mill or a lathe. Of course, the 3D printer can handle them, so they're a super easy way to join a couple different separate bodies. You can just quickly define the profiles and join them together. And lastly, anyone who's modeled plates before, things like that, knows what a fillet is. It's a pretty simple idea. But what a lot of people forget is when it comes to 3D printing, you can fillet anything you want. You can fillet everything if you want to, every corner. And so it's a habit of mine that after I model a 3D printed part, I'll just add a little fillet to all the interior corners. Every place there's a corner coming in like this, you add a little fillet. And it actually really does improve the strength of your part just by adding in these fillets. So it's a habit that I'm in, just to go through and fillet everything before you print.
All right, so there's a bunch of different variables that come into play while 3D printing. The first one I'm going over is layer height. So the layer height is how thick each layer is, and there's no general rule for how it improves strength. It's a parabolic function. So if you go really short in each layer and your layers are much smaller than your nozzle diameter, you end up with a lot of fusion. There's more fused layers, but those fusions between the layers are weaker than just these strands of extruded plastic. So if you go too small with your layer height, it's weaker than if you go with a medium layer height. But then if you go with an even higher layer height, you end up with not enough adhesion between layers, and you end up with stress amplifiers between them. So that ends up weaker also. So there is kind of a golden, Goldilocks spot that you guys want to aim for, and you'll have to figure that out through trial and error with your printer and the materials you're using. Wall thickness is critical to the strength of your part. And the nice thing about 3D printing is you can increase the wall thickness or decrease the wall thickness at any area you want. Whenever you have a bolt or feature that's going through your part, you're going to want to use a thick wall. What else? Another thing to keep in mind is you should be keeping those walls as a multiple of your 3D printed nozzle size, because if you don't, you end up with a bunch of weird overlaps while you're printing, where the printer can't actually define where to go. And that's more important when you're printing thin than when you're printing thick. When you're printing really thick, it doesn't become that much of an issue. And then in terms of infill, there's a couple of variables. The first one is density. So if you guys look at the infill here, there's a really low density, a medium density, and a high density. So when you're really low density, you're gonna have the weakest part. But then as you get to medium density, it's fairly strong. Let's say this one's 50% density and this one's 75% density. By increasing from 50% to 75%, you're not actually going to gain that 50% increase in strength. You're going to end up gaining like 10%. So the higher your infill gets after a certain point, you end up with large diminishing returns. And then infill pattern. Here's a couple of the most popular ones. There's the standard rectangular one, or also called crosshatch. There's the triangular, and then there's the honeycomb. So with the first one, you end up with pretty good strength in all directions. My personal favorite is the triangular one, because if you look at it, you actually end up with the most strength in the direction of your faces. And then the honeycomb one, it saves time and it's pretty light, but you can think of it as a lighter version of the triangular one. It's not as strong, but as you can see, you can construct honeycombs within the triangular one also. This one's really good for saving time.
Okay, so this is one that's a little bit specific to high-end printers, so I don't want to spend too much time on it, specifically the Markforged in this case. But basically, if you're careful about how you do it, adding a few thin layers of reinforcement, so these reinforcement materials are carbon fiber, fiberglass, or Kevlar are the most common ones, you can really increase the overall strength of your part, just with a few thin layers. And there are two general kinds of reinforcement. There's concentric reinforcement, which is where the printer will add, rings of these, reinforcement materials around the outside of your part. And this does a couple things. It increases the strength of your holes if you have some holes going through there, and the strength of your walls on the outside. Or you can add layers of, whatever reinforcement material you're using. And these layers can stiffen the part from flexing perpendicularly. Another cool thing is you can usually define the angles that you want these layers to be, printed at, these materials, just so that, it can be stronger in one direction than other directions. So for maximum efficiency, the best way to do the reinforcement material is doing what's called a sandwich panel. So if you look at this diagram right here, the idea is anytime you're flexing a part, anytime you're trying to bend it, you're always going to have the most forces at the very top and the very bottom of your part. It's where the most compression and the most tension is going to be. You can kind of see that in this diagram here. And so in general, you want to be maximizing your material. So if you add a thin layer of reinforcement material at the very top and a thin layer at the very bottom, that's where these forces are going to be the strongest. The material is going to be doing the most work possible. And it can really increase how stiff these parts are. So up to this point, we've mostly been talking about tips for how to design successfully for 3D printing. But for the last couple slides, I want to talk about where in FRC are really the best applications for 3D printing, where I think that 3D printing offers like a really outstanding solution to some common FRC problems. So the first one is fast iteration. And when I say this, I don't mean like prototyping at the beginning of the season. Because a 3D printer is never going to be able to keep up with a couple of mechanical kids with hand drills and wood screws. It's just not going to be viable. But later in the season, you might have some complicated parts that you need to iterate on kind of quickly. And this is where 3D printers are really excellent. So an example of this is these were the pulleys on our climber on our robot last year. And we had to adjust the size of these pulleys in order to get our robot to climb up evenly. Or else it would tip to one side and potentially tip one of the robot on a ramp off. And so as you can see, these are kind of complicated parts. This is not the kind of thing that a kid on a lathe can knock out in an hour. This would waste a lot of material if we tried to do it on a lathe too, because they have those big flanges on them. But by doing it on a 3D printer, we could just print these overnight and come in the next morning and throw them on the robot and verify whether they work or not, make some adjustments, and do the same thing the next night. And so it was, for kind of this later in the season iteration, it was a really great way to quickly change these complicated parts. So two of the most common uses of 3D printing that on our team at least is electrical mounts and sensor mounts. So there are a couple good reasons to develop an electrical mount for some common electrical components on your robot. Number one, you can group similar components together. If you look in that picture right there, that is a PCM, a manifold, and a bunch of solenoids all in a single module that you can just slap on the robot. You can free up some belly pan area. So by taking that PCM and moving it vertically, we free up a little bit of space, which kind of reduces some constraints on other areas of design. You can have more mechanisms kind of encroaching on that space. And lastly, it makes the electrical team's life a little bit easier because they can have these modules pre-assembled, and they can have wire strain relief, zip tie paths, and all these fancy features, and they can just throw it on the robot. And electrical mounts are a great thing to develop during the off season, in my opinion, because you're not constrained by time. You can take the time to add all these fancy features, and you pretty much know what electronics are going to go on your robot, the off season before. So it's a great time to do it. And then another great application is sensor mounts. So more often than not, the places that sensors are really needed on the robot are always the worst places to mount to. They're always going to be around moving components. So maybe this is a gearbox, maybe this is a moving arm, that kind of thing. And these mounts need to be rigid, accurate, easy to mount, and they need to reach awkward places sometimes, it's not an easy problem to solve. But 3D printing can meet all these requirements with some smart design. So a great example is with mag encoders here. Of course, I don't know how many of you are familiar with mag encoders, but they need to be held rigid. They need to be accurate in the right spot every time. And by 3D printing them, you can make a pretty strong mount that you can just throw these on. That'll be a lot lighter than aluminum anyway. So, and of course, they can reach awkward places too. So I've found that 3D printing sensor mounts is a great way to do it. So printing pulleys too is a great way to save a little bit of weight on your robot, especially in low torque situations like intakes, where the pulleys aren't going to be doing a whole lot on their own. If you just replace those aluminum ones with 3D printed ones, it can really save a lot of weight. This is the one place where you can actually 3D print power transmission and kind of get away with it. And you can do it on large pulleys too, where there's not going to be a whole lot of force in the individual teeth because there's so many teeth, and maybe there's not going to be a hex profile in the middle. There'll be, in this case, a bolt pattern around the outside. I already shared with you guys that the pulleys on our wrist earlier this season just totally failed. So you got to be careful with this, because obviously if you're putting 3D printed parts in places where there's a lot of torque, there's a chance they're going to fail. And kind of similar, I think dead axle plugs are a great place for 3D printing too. So for those of you who are unfamiliar with what a dead axle is, the idea is, just as it sounds, you have a stationary axle going through the middle of some moving components, and then parts that are rotating around that stationary axle. They can be as simple as, a pulley with some bearings in it, or they can be pretty complicated. And they have several advantages over live axles. So, sending some thunder hex through, some bearings. They allow you to, support the plates with the axle themselves. They can define the method of power transmission. So down here, this was the drum on our elevator earlier this season, and this was pretty long. This is about this big. I wouldn't necessarily want to be putting torque through a hex profile that was this big. There was, the elevator needs to be pretty powerful. But instead, the shaft here going across is not actually taking any of the torque. It's not doing anything except for just supporting it. All the torque is going in this big, beefy 2-inch tube around the outside. And so by defining the power transmission that way, we were able to make it a lot stronger than we could than with just sending hex through the middle. And dead axles can also have parts moving around them at different speeds. So you can have an arm and some pulleys going around the same shaft at the same time, but moving in different speeds. And so dead axles are not specific to 3D printed parts. They can be used anywhere, but sometimes 3D printers make it kind of worth the added complexity. Because you can just print, a single plug on either end that has all the, power transmission, the pulley, all the bearing holes already inserted on the part, and you can just throw it together and really quickly mount it, and it's super easy to do. So 3D printing makes it sometimes worth it. And then this last slide is also a little bit specific to high-end printers, so I'm not going to spend too much time on it. But it's a common problem in FRC to have kind of tubes being joined at weird angles. That don't line up nicely. Maybe so some common solutions to this are using bent gussets, bent aluminum gussets, or maybe a tapped aluminum block in the middle. But neither of these are really great solutions. They all have their limitations. But 3D printers can offer an alternative to these that's super lightweight and oftentimes strong enough. Because of course when it comes to 3D printing, you can have any weird angles that you want of tubes being joined at, and the printer's always going to be able to print at those weird angles because you're not limited to orthogonal lines. But this is one application where you really need to think about print orientation and print settings and all those things I talked about earlier, because of course, if you're joining tubes, you're probably gonna have some forces going through these parts, and you really don't want these parts to fail. So anyways, those were the areas that I kind of see 3D printing as having the most potential in FRC. But hopefully you guys can think of some other ideas, and I encourage you guys to design some things for your own teams that I can go back and steal later and I don't know our own robot. But anyways, thank you guys for listening. If you guys have any questions, I'll probably be hanging around here for a little bit later, or you guys can send an email to 1678 Mechanical, and I'll respond to you guys. And then one last thing, this is a QR code where if you guys have any questions or want to take a quick survey and help us out with some feedback a little bit too, I encourage you guys to scan this and take the survey, because it really helps our media team out. Thank you guys for listening.
Can you go over the print